Hello everyone, my name is Augusto, and I will be presenting our paper, A Systematization of Knowledge on the Security and Privacy of Blockchain Interoperability. This is a joint work with Rafael, Andre, Miguel, Luyao, and Thomas. So the first question we should try to ask ourselves is, what exactly was the motivation to do this work? Well, I think the number kind of speaks for itself. Since June 2021, around 3.2 billion US dollars have been stolen from cross-chain bridges, which are a specific interoperability mechanism. If we do the math, which is not really complex, this gives an average of $3 million stolen per day since the date of the first hack until the date of presentation, which is in the bottom of the slide. The second question is, all right, were this 3.2 billion US dollars originated in one, two, maybe three isolated events? Well, the answer is kind of simple. It's not really. We have a frequent problem, and as we can see in the figure, even those smaller bubbles are usually in the order of at least $1 million. Additionally, we found out security and privacy, and especially privacy, are completely understudied in this area. No one really knows what exactly privacy means. Additionally, the guidelines for developers to build cross-chain solutions are just too vague, which causes different solutions being produced, being designed with completely different architectures in an ad hoc basis. So in this paper, we propose a security and privacy model for cross-chain. This includes relevant properties and approaches to guarantee both security and privacy. We classify interoperability mechanisms in the literature and then select a set of vulnerabilities, leaks, and attacks, and analyze real-world hacks that happened since June 2021 and point some future research directions based on that classification. All right. So what exactly is blockchain interoperability? Well, I really like this quote that says that it is the ability of a source blockchain to change the state of a target blockchain or vice versa, enabled by cross-chain transactions spanning a composition of blockchain systems. So it's basically a mechanism that enables or facilitates communication between two different blockchains in a way that we can transfer data or assets between different blockchains. So what we did was analyze 242 studies. 58 were retrieved from Google Scholar using a search string using relevant keywords. We have 10 audit reports and 63 gray literature documents, and we needed to rely a lot on this kind of information because of the unstructured practices in the area, like blockchain, the Web3 ecosystem as a whole. So for the security model for cross-chain, the first thing we do is capture the relevant properties for a secure interoperability solution. The first thing, before going into the different properties, we divide the layers of a cross-chain solution into different relevant layers. At the bottom, we have the network layer, which is basically the different consensus mechanisms of the underlying chains, the smart contract engines, and so on. We have the protocol layer concerned with the architecture of the interoperability solution, the architectural trade-offs between security, decentralization, and performance, for example. We have the implementation layer concerned with the development of on and off-chain components, and then the operational layer concerned with key management, infrastructure monitoring, code upgrade, incident response, and so on. So now diving into the properties. So we base ourselves on the CIA triad. And instead of having confidentiality in the middle, we replace that with accountability. So we end up with the integrity of the system, the data and assets the system interacts with, accountability, the accountability of participants, either for good or bad behavior, such as integrity breach attempts, and then the availability of processes and systems to relay information, to relay proofs from one blockchain to the other. In the paper, we select a set of security approaches that each of those guarantee at least one of those properties I showed in the last slide. So the first and really straightforward one is centralized centralization, a centralized party that facilitates communication between blockchains. Then we have, for example, validity proofs using zero-knowledge technology. We have fraud proofs that are based on optimistic windows, and proofs are optimistically accepted. And we have watchers that have a time window to challenge the data that was relayed by those relayers. Finally, we have secret and time-based locks, which are usually relying on off-chain communication channels, and parties communicate directly with each other, and the security of that channel, the security of the cryptographic primitives are basically the security of the whole interoperability solution. And we have more in the paper. So we did exactly the same for privacy, right? So what exactly, the question we're trying to answer is what exactly does a privacy or does a private solution mean in this context? So the first property is the unlinkability of transactions in different blockchains. So we have one transaction in blockchain A, one transaction in blockchain B. Is it possible for me to identify that these two transactions belong to the same cross-chain transaction? Then we have the anonymity of users and operators of the interoperability solution. And we have the confidentiality of cross-chain transactions. Can I see the content of these cross-chain transactions? So we have some privacy approaches that we explore in the paper, such as zero-knowledge proofs, trusted execution environments, a set of digital signatures, such as adapter signatures, blind signatures, ring signatures, and homomorphic encryption. All right, so based on these models for privacy and for security, we classify 57 interoperability mechanisms. Here I have 4 insights from that classification, right? From those 57, around 6 are from the industry, and the total value logged of those 6 is around 75% of the total value of the market. And the first insight is that security takes precedence over privacy. In the industry, protocols that dominate over 75% of the TVL completely neglect privacy. And this is connected to the second insight, that is saying that these privacy-preserving features usually bring considerable overhead to interoperability mechanisms, which we identify here some kind of trade-off between privacy and scalability or efficiency, where these protocols might not be able or might not be interested to sacrifice efficiency for providing these kind of features. Then we have cross-chain and linkability in asset and data transfer-based protocols. It can only be guaranteed when the underlying chains ensure some kind of confidentiality, either because they are private chains or they're public chains with privacy-preserving features such as Monero. Finally, we have stake-slashing mechanisms as the predominant trend to guarantee accountability, and a smaller subset relies on the legal identification of parties, for example, using KYC primitives. This is usually done in more centralized frameworks. All right, so based on those 242 studies, we collected a set of vulnerabilities, privacy leaks, and attacks. We classified them based on the layer that they appear. We have this divided on operational implementation, protocol, and network layer. And then in orange, we have the privacy leaks. We have a high incidence in the protocol layer, then implementation layer, and then only 3 vulnerabilities in the network layer and operational one. So the main takeaway I would like to take from this slide, of course, there are a lot of vulnerabilities in the protocol layer. But the interesting thing here is that in this theoretical research, we only found 3 vulnerabilities in the operational layer, which completely contrasts with what we see in cross-chain hacks, and I will show that in a couple of slides, right? Where this layer has a lot of incidents in terms of vulnerabilities and exploits. So we map each of these identified vulnerabilities into a set of mitigations in the paper. What we also do is collect 18 cross-chain hacks that happened in the past. We classify them based on a set of criteria. And of course, this table is kind of complex, so I will divide this into the criteria, zoom in a little bit into the criteria. So we have the security approach, date, the amount that was stolen, the type of attacker, black hat, white hat, the number of transactions used to conduct the attack, the usage of transaction mixers to launder funds either before or after the attack, to obfuscate the origin and destination of funds respectively. Then we have incident response related metrics such as the time it took to discover the attack internally, the time it took to communicate the attack to the exterior, to the users of the interoperability mechanism. And then we have the location, where the vulnerability was found and where the exploit location was. And usually the exploit is on chain, and the vulnerability might be off chain or might be on chain. And then we map all of these attacks to theoretical vulnerabilities and what are the vulnerabilities behind, or what were the vulnerabilities behind each of these hacks. Right. So we also retrieve a set of insights from this classification of hacks. Right? The first one is we see that there's a lack of incentives to disclose vulnerabilities. Right? Only 35 million were returned by white hats. This is around 1.5% of the total value stolen. The second is that the lockman pattern in cross-chain bridges is riskier than others, and 62% of the total value stolen was drained from the escrow. The escrow is basically the amount that is kept locked on the source chain when we're bridging to a target chain. Right? That escrow becomes the honeypot for attackers. We have hackers using mixing services, transaction mixers, to launder funds either before or after an attack, 5 times and 11 times respectively. And we have $1.6 billion stolen due to inadequate key management, for example, vulnerabilities in the operational layer. Inadequate key management is one of them. We also point some future research directions from this work. For example, the proactive monitoring of cross-chain systems. It's important to monitor and identify breaches or breach attempts. We have also connected to this is the incident response frameworks are not really there for generic cross-chain systems. No one really knows what to do, the steps to follow when such a hack or an attempt exists. We have maximal extractable value, or specifically front running, as a possible defense strategy for cross-chain systems. And then we have contributions to standardization bodies such as ISO and IETF that are working on standardizing the communication between two different blockchains. So it's definitely a good contribution. So to conclude, what we do in this paper is basically take the amount of hacks as a motivation and the frequency of these hacks as a motivation to conduct a systematization of knowledge. We identify the relevant security properties and approaches in cross-chain. Exactly the same for privacy properties and privacy approaches to guarantee those properties. We extract insights from the classification of interoperability mechanisms in the literature, both academia and in the industry. We collect a set of vulnerabilities across relevant layers. We explore previous attacks and what we can learn from these attacks to avoid them in the future. And then finally propose a set of future research directions for people to follow as a result of the systematization. That's all. Thank you very much for listening.